The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so do you guys understand what's going on? Right? Okay, so there's like bacteria here, and in a duplication process, it can either duplicate or die, right? And that's just for one bacteria. So you have like two, then that one remains unchanged. That make sense? Okay. So question one was, what does assumption 2 mean in terms of percentages? What's the probability that a cell will duplicate, and what's the probability that a cell will die?
What?
Louder. Huh? Yeah, so 1/2, right? So this is 1/2, 1/2. That's all that question is asking.
Actually, it's 0. Or if you're 4.
Yes, but this is just for assuming an initial state of 1. Anyone for question 2? Give me an example of a chain where the bacteria neither reaches n equals 0 or n equals 4.
It succeeds and it fails, it succeeds and it fails, it succeeds and it fails forever.
Wait, what?
It succeeds then fails forever. Like succeeds, fails, succeeds.
Yeah, so like an example of a chain would be,
1, 2, 3.
yeah. It can also go from like 1, 2, 3, 2, 1, etc., right? Okay. So that's pretty easy. This path right here is called a trajectory in terminology. And attainable, if you guys read that, means that you can reach a certain state from another state. So we can reach like state 3 from state 1. You can't reach state 3 from, say, state 0. So that means unattainable, right? You can't have bacteria if it's not existent. Okay, so for question 3, did anybody get 5 generations? Okay. Anyone for 4? Yeah, so it's not possible. So you need to make sure you get your problem space correct. Because some paths cannot exist and some can. So that's an important part of defining your model. And if these aren't clear to you, then you need to redefine your model. Okay. All right, so question 4. I know a lot of you guys asked, it's my fault. Transition probabilities are the probabilities that you can reach a state to another state in just one step.
Oh.
Yeah, so if I give you, like this is a transition probability. So this is telling you the probability that you go from state I to state J. And I or J can, which is what M was, can be either state 0, 1, 2, 3, or 4. So what I'm asking you is like the probability that you go from state 0 to state 0 is, or the probability that you go from state 1 to 0, or the probability that you go from like 1 to 2. Stuff like that. So for these transition probabilities, can anyone tell me what this is? Yeah.
Or we just look at it.
Yeah. Okay. This one?
What are the numbers?
Yeah, I can't read the number.
Oh,
Can't see that.
1 to 0. 1/2, yeah. 1 to 2 is 1/2, right? And then 4 to 4 is unrealistic, but for this problem, it's going to be 1. Okay? So that's what it's asking you. Question 5 is more of a thought answer. So Did you guys read beforehand the concepts? How that affects it? Okay.
Wait, what's the difference between the two concepts?
Right, so I was asking that. Okay. So the first one is referring to not the actual states, but more like your actual problem. Like, so how the bacteria actually changes, if that affects your problem.
Oh.
But the second one is just based on like the number,
Okay.
which is your state. Okay. So for this model to work, if you're at state 3, then it doesn't matter what states you were at before 3. What only matters is that you're at state 3 right now. Okay, so does that make sense?
Yeah.
Okay.
So that would be number 2.
And that's called the Markov property. Okay. So you guys figure out question 6 at all?
What's question 6?
So transition probabilities are going from one state to the next in one step, right? But now I'm asking, what are the probabilities 2 steps? So I'm going to do 6, 7, and 8 at once then, because that's answered better using matrices. You guys have this diagram already, right? It's not labeled, but it's the 4th figure, I think. Yeah. You guys have this, right? Okay, so this is just for one step. But did anyone figure out how to get it, this matrix for 2 steps? Yeah.
Where did you get the same thing that I got when I actually did it out?
So you mean multiply it by itself?
Yeah.
Yeah. So that would get you the second. So I'll just do that out then. Can you just go up?
Oh, it's an eraser.
You want an eraser anyway? Okay, I'll just do it here. Okay. So you guys.
There's one right there.
And this one? It's just stays.
No, like, yeah, push that one, the one you're holding.
Yeah. Way up.
Is there one right there? Where'd it go?
Yeah,
I
I
don't know
used
where
to
it
have 3. Oh, here it is. Okay. Huh. Okay. So, quick review. Do you guys know how to do matrix multiplication? You already know. No? No? Okay, I'll just go over it. Well, because some people. Okay. So for you guys who do know, what's this? Huh? Right? What is it?
Oh, okay.
This row is column that. This row is column. Right? So AA, BC, AB, BD. Right? Okay. So which one is? D. Anyone get that? Kind of. You'll get it more if you see numbers. Okay. So we have for our case P00, P11, etc., etc. So if you multiply it out, like together, then what do you get? You get like POO times POO, right? Anyone tell me that? What's next? Right? Yeah, I'm just gonna do the first two columns, the first two entries. So you can just multiply it, but you need to understand why that works. So this tells you how it works because it goes from 0 to 0, 0 back to 0, right? Which is what you want in 2 steps. And then this is 0 to 1, and back to 1 to 0, just 2 steps again, right? Same thing for 2, 0 to 2, 2 to 0, etc. And the second entry is the same way, except you have a different initial state. So 1 to 0, 0 to 1. Or wait, 0 to 0. Does that make sense to everybody? Okay, so if you just follow that same formula, you'll get it for every initial state and every end state in 2 steps. And the easy way to do that is to just multiply the matrix. So easy. So Pn means this transition probability matrix for 1 step times the number of steps. So to get the number of 2 steps, you would just times it by itself. 3 steps, you just times it by itself, etc. So does anyone have a calculator? You? Okay.
I've done out a matrix with 2 steps.
Okay. The question I want to answer though is if any of those values converge if n is large. So if you multiply your matrix like a million times, does it converge? Like, do these numbers converge or change? Okay.
Eventually go to either 0 or 4.
Yeah.
So that's
I have
what you
5
think.
by 5.
Right.
So this is multiplied
Because the
by 5.
probability would keep decreasing, we have a trajectory going further, that should, the limit of that should be 0. And then you'd, all you have to do is, have like, you should have 3 fourths and 1 fourth. You started at 1.
So you're getting there. But the matrix will tell you for every single possible step, like every initial state, every end state. So if I ask you like, the probability that you can go from state 2 to 4 with n in, or 2 to 3 with n equals forever, then what would that be? Then that's a little harder, right? So then you have to multiply. Wait, all the different combinations.
Have to do it, but like you'd say, hey, this is gonna, this thing that would fail completely in this number of steps, on this step, work out how to take the limit. So there's a couple way that, like mathematically, happy with.
You know, you might be right, and I would have to read more. But right now we're just doing it like this way. But I can get back to you if you want that. Did you get it yet?
Well, how many times do you want me to do? I just did.
Just until the values converge.
Until they converge, okay. Give me a second.
Like, because n is relative.
Do I need to know how many times?
Well, it'd be nice.
Oops.
It's okay.
I haven't even sure.
That was fine.
I'm just pressing the enter button and see.
It's okay. Converge means like the values stop changing, right?
Okay, which value?
All the values in the matrix. So,
Well,
you
the
know,
first column stopped.
right. How about the rest?
Not yet.
Not yet? Okay. And you can do it to like 2 decimal points. That's fine.
What's weird is the second column, the numbers keep fluctuating.
Second column?
Yeah.
That means they don't converge, right?
Cool. So yeah, they don't converge. But the first column does. Wait, let me check the third column. Oh wait, no, they do. It's just getting really close to 0. I didn't see that you said -29.
Okay, then I do.
Yeah, sorry.
That's fine.
Whoops. That's why I didn't know the school.
Oh, you're right, because it's E to the.
Yeah, I didn't see that anymore. Hey, it looked like they were going from like 1 to 3.
Okay, so you do have a value?
Yeah.
Okay, so what's your matrix?
Okay, this is gonna take a while. Let me get back to the beginning. Okay, 1,
Mhm.
0, 0.
You can go like by column.
Oh,
Might be.
okay.
Yeah.
Wait a second. Okay, 1.75,
Mhm.
0.5, 0.25, and 0. And it's 0, and then 0. These are basically 0.
Yeah.
All the way down. And then 0 all the way down. Well, 0, 0, 1, 0, 0.
This one?
Yeah. I think so. Wait.
No, this is
that's
0.
That's 0.
Yeah.
And then all zeros again. And the last one is just the first one reversed. So 0.25, 5, 0.75, 1.
Okay, so does everyone see what this is saying? Basically, if you repeat this experiment for n equals forever, or some really large number, then you can figure out a probability for this entire model that you can go from like state 0 to 0, state 1 to 0, state 4 to 4, or state 3 to 4, etc. So from your initial problem, you only know that it's half, 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 and you have no idea really how the experiment's going to end up in the long run. But if you do this, then you can see, oh, well, if I start off with 3, then I have a greater chance of ending with 4. I have a 75% chance of getting to n. But if I start like initial state 1, then I have, in the long run, 75% chance of dying out. So this tells you like all the possibilities that can happen if you run it over and over and over. Does that make sense? So the important thing to notice is that your initial state does matter in how it ends up, even if the probabilities seem pretty much the same initially. Okay, so that's question 9, I think. Yeah. So a Markov model is illustrated usually in this way. So you'll have the states like this. And then you'll draw arrows that represent the probability. So like 0 goes back to 0, probability of 1. And then 1 to 0 is like 1/2. 1 to 2 is 1/2, etc. So this is a new way of describing your problem space, right? This is what's going on in your entire model. Because unlike before where we had specific outcomes, you could like figure out the probability of each, this one keeps alternating, right? So that's basically what it's trying to tell you. And if you guys did read it in here, I think it tells you that states 0 and 4 are called absorbing states because that's where ultimately your experiment will end up, right? So they're like endpoints for this model. Okay, so does that make sense to everybody? So, number 1, did anyone get an answer?
How many kids?
Yeah? 100%. Yeah. Did everyone get that?
Yeah.
Everyone understand it? Yeah. Anyone want me to go over it? No. Okay. So that's an easy one. Okay. 2.
About 81%.
Can you give me in fractions?
95 times 94 times 92 times 92 over 100 times 99 times 98 times 97.
Does everyone get that? So, right, because there's 95 non-effective ones. And then every time you choose one, you have to take one out. Okay, does that make sense to everybody? So is that hard, easy, medium?
Wait, shouldn't there be one? Oh, no, that was just one. Mine. I can't remember.
Is this harder than the last one? Yep. A little harder?
Because that one was easy.
Just curious. Okay. 3? Anyone got an answer?
2/3.
Yeah. Did you get that too?
No. Let's go.
Okay. Well, I'll go over it then. Okay. So there's 4 combinations of kids, right?
It's just like that door code.
So use your brain.
Ah. Right? I get it. You get it now? Okay. So if they have a boy, it can't be this. And then there's 2/3 chance that he has a sister.
It is because we have the same thing, like the girl and the boy on the opposite.
Oh, okay. Yeah, so it's different. Because it matters which order he can.
It's still really confusing because if it's about meeting the boys, in the third example, you wouldn't have met the boy.
Why not?
Hmm?
They're both born and they're both alive, so you could have met either one. It doesn't matter if they're older or younger.
Yes, but with the 2, then you'd have 50% chance of meeting the girl. Like with boys, then you'd have 50% chance.
But there's no chance whether you're meeting either one, because I'm telling you you are meeting the boy.
Right.
Yeah.
Yeah.
So it's an assumption, right?
I don't know.
Is someone's cell phone over there, or is that just like...
No, that's the other room. They're playing Cindy Lauper.
What?
It's kind of.
Where is this other room?
That's odd. 4?
45%.
Oh, I didn't calculate it, so if you
Oh.
did the way to do
0.3
it.
times 0.5
Okay.
plus 0.4 times 0.25 plus 0.8 times 0.5.
So what is that? What did you say?
0.45.
Right, so you shouldn't play, because you lose. Okay. Yeah?
8 times 75.
Oh, sorry. Okay. Yeah.
In other words, 8 million.
Does everyone understand this? So you only have 8 options for your first digit, and then for the rest, you have 10 options.
Zero. Oh, it's 0. Yay!
Does that make sense? I forgot to ask. So 3, easy, medium, hard. Medium?
Yeah.
Hard. Okay. How about 4? Pretty easy. Okay.
What?
5? So for 6, anyone get that?
Hard.
So PMF is basically like the probability that your random variable can be a certain event. And I'll kind of explain that. And I'll upload the file so you can look at it. Okay. Did anyone get 6?
Well, I didn't know what PMF was, so that's kind of a problem.
What's it called?
It's probability mass function. Okay. So okay, so this is hard. Okay. I see. Do you remember this one? You know, you have
Oh.
Oh.
Kind of, yeah.
That thing, you have to memorize.
Oh. Yeah, I don't remember that.
okay. This is a binomial, right?
Yeah.
Okay, yeah. Okay, good. So to answer your question, since you weren't here, K is like the different numbers that your random variable can take, right? And this is a probability that you get that. So this is just a formula for saying what your probability would be. So if I give you this, would that be a little easier? You can figure out what n is, what k is.
Wait, K is 0.01, right? No, P is 0.01, right?
Yeah. So P is 0.01.
I'm assuming N is 1,000 because N minus K needs to be positive. So then K would
So
have.
k equals from 0 to,
Right?
wait,
49?
yeah. Hold on.
Wait, wouldn't it be 1 to 50? Or,
I think. I have to double check that. I think that's right.
Why would it be 0?
So, okay, let me read this again. So you have 50 modems for 1,000 customers, but you can't have a K greater than 50 because you only have 50, right?
yeah.
What? Yeah. So that answers your
Why
question.
can't you have 0?
Because 0 isn't.
Oh, wait.
Wait, which modem
that
would
make
be labeled
sense?
number 0? It says there are 50 modems, so it'd just be 1 to 50.
Yeah, but you couldn't be using none of the modems.
Yeah, you're right. So you can, like, maybe none of the customers need it. So,
Oh.
yeah, you're right. Thank you. So it can go from 0 to 50. Okay? And then n is 1,000 because that's the total number of customers. Okay, so that would be okay. So does that make sense? If I give you this, is that easier?
Yeah, sort of. Yes.
Okay, so it's hard. Okay. Do you guys understand any other questions?